So this is another video in my sequence of math foundation videos. This one is about proper subsets, set differences, and symmetric differences. So to begin with, we start with the topic of proper subsets. So you probably noticed in the last video that if you take any set, it will always be a subset of itself. Because remember, a set is a subset of another set if every member in the subset is a member of the superset. So for any set A, we can take it. Every member of A is always also going to be a member of A. So A will be a subset of A. This all seems kind of silly, right? It seems like we need something a bit more precise. And so there is such a thing, and it's called proper subsets. We say that B is a proper subset of A if every member of B is also a member of A, that is, B is a subset of A, but also we have B not equal to A. So what is that telling us here? That's telling us that every member of B is a member of A, but there's something in A that's not in B, because if A was a subset of B also, they'd be equal, and we're saying they're not in the case of proper subsets. So a quick example, we have here the set 1, 2, 3, 4, and it's a proper subset of the set containing 1, 2, 3, 4, and 5. Why? Look here, 1 is here, 2 is also here, 3 is also here, 4 is also here. So this set is a subset of this set. But also they're not equal because this subset, or this set rather, is not a subset of this set because 5 is here and 5 is not here. So the subset symbol, it really only goes in one direction here, right? We only have the subset in one direction, not in both. And so this set is a proper subset of this set. So moving along to set differences. Set differences are sort of like subtraction, but we have to sort of generalize what we mean by subtraction since we're not dealing with numbers here. So I'm going to start with the definition, which usually I like to start with examples, but I think it pays a little bit with this in this case to start with the definition, and then we'll do some examples. So if we have two sets, A and B, A minus B, which is also sometimes written like this. Sometimes people write a slash instead of a minus. It's the set of all things that are in A and aren't in B. So to be in A minus B, you have to be in A and you have to not be in B. So for example, we can take the set 1, 2, 3 and make that our A. And we can take the singleton set B containing 1, okay? And so if we take the set difference of these two sets, we get 2, 3. Why? Because I start here, the set of all, this here, to be in this set, you have to be in A, but not be in B. So 1 is in A, but it is in B. So it's not going to be in the set difference. That's why one's not listed here. Okay? 2 and 3 are both in A, and neither are in B. So they're going to be in the set difference. Another example, we take again A being 1, 2, 3, and this time I'll take C to be the singleton 4. Okay, so here 1 is a member of A and it's not a member of C, so it's there. And the same with 2 and 3. 2 and 3 are both members of A, but neither are a member of C, and so they're in the set difference. Well, what about this 4? Well, it's irrelevant because 4, even though 4 first of all, it would have to not be in C, but in any case, 4 is not a member of A, so we don't even have to think about it. It's not in. Okay? So moving along now, we can remember Z is the set of integers and E is the set of even integers. So if we take all the integers and we subtract away the even integers, what's left is the odd integers. That seems fairly intuitive, but let's make sure it's coinciding with the definition we just made. So every odd integer is an integer. That's the first thing. And every odd integer is not an even integer. You can be even or odd, but not both. So this definitely is the set difference. Okay? Another example, we can have the pair set containing the numbers 1.5 and 2.5 and subtract off the set Z. So that's Z again is the integers. So here 1.5 and 2.5 are both in the set difference because they're both members of the set. I'm going to call this set A again, even though I've used A elsewhere on the page. So they're both members of A, and they're neither of them are integers, so neither are members of the set we're subtracting off. So they are definitely in there. Okay. So moving along, I wanted to get a couple of set difference examples involving the empty set, because sometimes people struggle with the idea of a set that contains nothing. Okay. So you can take any set, and if you subtract off the empty set, you get the set back, the original set back again, right? Why? Because every member of A is a member of A, and every member of A is not in the empty set, because there's nothing in the empty set, okay? So if we take the empty set and we subtract A, okay, we get the empty set. Why? Well, every member of the empty set is in the empty set. In particular, there's no member in the empty set, so that statement is true because we don't even have to check it because there's nothing to check it on. Okay, so every member of the empty set is a member of the empty set, and every member of the empty set is not a member of A. Because if there were a member of the empty set that was a member of A, then that would mean there was something in the empty set, and this whole thing would be a contradiction, very strange. It doesn't work out, right? So empty set minus A is equal to the empty set. So stepping away from formalism for a second, imagine I have an empty bag, and then I have a bag filled with some various things, right? Okay. So if I say I look in my empty bag and I say I'm going to take away everything in my empty bag that is also in the bag that has some things. Well, what you would have left at the end is still just the empty bag. Okay? So finally, I have the natural numbers and I have the integers here. And so I'm taking the natural numbers and I'm subtracting off the integers. So if I subtract off the integers, remember that the natural numbers are a subset of the integers. They are every non-negative integer. So every non-negative integer is also an integer. So there can't be anything in the set difference, because if there was, that would mean there was something that was a non-negative integer and also wasn't an integer. There is no such number. So the result is empty. Okay? Finally, I'd like to talk about the symmetric difference. So now that we have set differences, we can talk about the symmetric difference. You also would have had to have watched the video about unions in order to understand what I'm about to do here. Okay, so the symmetric difference is a special operation on sets. A symmetric difference B is the set difference of A and B in union with the set difference of B and A. Okay, so probably the best way to do this is to compute an example, and then you'll see what I mean. So I'm going to take the symmetric difference of these two sets, the set containing 1, 2, 3, 4, and 5, and the set containing 3, 4, 5, 6, and 7. So first, I need to find the set difference of 1, 2, 3, 4, and 5, subtracting off 3, 4, 5, 6, and 7. So the set difference in this guy is going to be 1 and 2, right? Why? Because 1 and 2 are here, and they're not here, so they're definitely in that set difference. And the only thing that's left in here is 3, 4, and 5, but that's also in the set that I'm subtracting off. So that means they don't wind up in the set difference. Okay? So flipping the order of the subtraction now, I take 3, 4, 5, 6, and 7, and I subtract off 1, 2, 3, 4, and 5. Okay? So 3, 4, and 5 are here, but they are also here, so they don't wind up in the set difference. Okay? Then I have 6 and 7 that are in my set here, and they are not in the set I'm subtracting off, so they wind up in the set difference. So the the symmetric difference is going to be the union of these two sets. So the symmetric difference turns out to be 1, 2, 6, and 7. So that's the symmetric difference. That's it for this video. In the next video, I hope to talk about power sets, universes, complements, and some other stuff. And further on down the road, I'd like to show you how you can create sort of like an interesting algebraic thing using some of these set operations. But that'll be in a later video. Thanks for watching. Stay tuned.